Welcome, everyone, to the Deep Dive. Today, we're plunging into a topic that really captures the zeitgeist of our technological era. This relentless human quest for artificial general intelligence, AGI, and maybe even artificial superintelligence down the line.
Yeah, and the pace, the sheer pace of advancement in large language models, LLMs, it's just been breathtaking lately, hasn't it?
Absolutely. We've seen these incredible leaps, with models like GPT-4o, Claude 3.7, Gemini 2.5. Each one seems to just push the boundaries of what we thought was even computationally possible for these kinds of intelligent systems.
And what's really fascinating, I think, in this whole accelerating landscape is the role open source models are playing. It's becoming increasingly pivotal.
Right. It's not just the big proprietary players anymore.
Exactly. While, the proprietary systems from the industry giants have definitely set incredibly high benchmarks, the open source community hasn't just been playing catch up.
No, they've been closing the gap fast.
They really have. They've been rapidly closing that performance gap and fostering this environment of pretty unprecedented innovation and collaborative research. So today, our deep dive is going to illuminate one of the, I think, most significant and recent contributions to this whole open source renaissance.
Okay, let's unpack this then. We're dedicating our time today to the Qwen3 Technical Report. Now, Qwen3, it's the latest iteration in the, well, highly regarded Qwen model family.
Right, they've built quite a reputation.
They have. And it's presented not just as a single model, but as this comprehensive series of LLMs that are really pushing the envelope. We're talking performance, efficiency, and also their multilingual capabilities.
Precisely. And this report, it's quite extensive. It gives insights into models that span a huge range from a, pretty compact 0.6 billion parameters, which could be great for more constrained environments.
Like edge devices, maybe?
Yeah, potentially. All the way up to a colossal 235 billion parameters for, really cutting-edge applications. And it details both the dense model architectures, the more traditional ones, and critically, these advanced mixture of expert or MOE architectures.
So Mo is a big focus here.
It is. And our mission, really, for you, our expert listeners who are deep in machine learning, data science, and mathematics, is to provide a comprehensive and professional overview. We're going to meticulously dissect the core concepts, the innovative ideas, and crucially, the empirical results presented in this really groundbreaking paper. We want to give you that shortcut to being truly well-informed on Qwen3.
And right off the bat, there are some advancements that just jump out, don't they?
Right.
Qwen3 introduces this unified framework that seems to seamlessly integrate two distinct ways of operating.
The thinking and non-thinking modes.
Exactly. A thinking mode for that complex multi-step reasoning,
Yeah.
and a non-thinking mode for, the quicker, more direct, context-driven responses.
And beyond just integrating those modes, there's this innovative adaptive resource allocation system. They call it a thinking budget, which is quite an apt name.
It is. And that, coupled with a massive expansion in multilingual support, seems like it could significantly broaden the model's global applicability and reach.
What's particularly innovative here, I think, is that these advancements directly tackle a common frustration for developers, right? The need to constantly switch between different specialized models for different tasks.
Yeah, that can be a real pain, managing multiple model endpoints and pipelines.
Totally. Qwen3 aims to just eliminate that friction by offering dynamic control over the inference process and unifying these diverse capabilities into one, more flexible system. It ensures highly competitive performance across an incredibly wide range of benchmarks.
So we're talking things like coding, math.
Yeah, everything from intricate code generation, deep mathematical reasoning, all the way to complex agent tasks. It's really about empowering users with unprecedented control and versatility, all from a single model.
That's definitely an ambitious vision. But, consolidating such diverse capabilities, that often comes with its own engineering hurdles, performance challenges. How effectively did they actually manage to navigate those complexities to get this level of unification?
That's the key question, isn't it? And it sets the stage perfectly for us to really delve into the core of Qwen3.
Okay, let's start with that vision. Section 1. The vision behind Qwen3, a unified framework for intelligence.
Right. So if we connect this to the bigger picture, these recent breakthroughs in foundation models, the ones we mentioned, GPT-4o, Claude 3.7, Gemini 2.5, but also things like DeepSeek V3, the Llama 4 series, they've really shown the incredible capacity these systems have now to distill vast amounts of human knowledge and, intricate capabilities.
They really feel like steps towards AGI, even if we're not there yet.
Exactly. They represent significant strides. But as impressive as they are, many still require a degree of, let's say, manual orchestration to switch between different problem-solving approaches. You might need one model for chat, another for analysis.
And we've definitely seen that trend towards highly specialized reasoning-optimized models too, haven't we? Things like OpenAI's O3 or DeepSeek R1, which are specifically fine-tuned just for complex logical operations.
We have. And what Qwen3 seems to be doing is attempting to consolidate these specialized capabilities right into a single, more versatile framework.
Which is ambitious, trying to be good at both the quick, intuitive responses and the deep, deliberate thought processes.
It is. And this isn't just about convenience, though that's part of it. It fundamentally changes how developers might design entire AI pipelines.
Yeah, instead of chaining multiple specialized models together.
Right. You could potentially rely on one smart system to handle both the quick hits and the deep dives, making the whole development process potentially more streamlined, more efficient.
Okay, so that's the goal.
Yeah.
How does Qwen3 position itself? What's its core identity?
Well, its core identity really centers around being open weight, highly scalable, and exceptionally versatile. It's presented as a collection of open-weight LLMs, intentionally designed to offer this broad spectrum of models.
Covering that whole range from 0.6B up to 235B parameters.
Precisely. From the very compact 0.6 billion, maybe for those edge devices or less resource-intensive tasks, all the way up to the flagship 235 billion parameters. This wide array means it can cater to an incredibly diverse range of downstream applications and also computational constraints. It sort of democratizes access to advanced AI capabilities across different scales.
And what's really interesting, I think, is how they achieve that versatility, especially at the top end.
Yeah.
You mentioned the flagship model, Qwen3 235B, A22B.
Yes.
That's a mixture of expert model.
Yes, it is.
So it has this massive total parameter count, 235 billion, which sounds huge. But the critical part, as he said, is that only 22 billion parameters are activated per token during inference.
That's the key to Mo efficiency.
Exactly. So this design, it's engineered to strike that crucial balance, right? Getting exceptionally high performance for complex tasks by drawing on the vastness of its total parameters.
While simultaneously maintaining remarkably efficient inference because of that sparse activation.
It's a major engineering feat, really, allowing for both that power and practicality.
It is. So let's delve deeper into these key advancements because they really form the pillars of Qwen3's innovation and why it's such a significant contribution.
Okay, pillar number one.
First, let's really explore the unified thinking mode and non-thinking mode. This is, I think, a profound architectural and functional integration. Qwen3 now incorporates these two distinct operating modes within a single model.
And it's not just like a switch you flip externally.
No, that's the point. It allows for dynamic internal switching between these modes without the user or developer needing to alternate between entirely different specialized models.
Right, avoiding that scenario where you use, say, a chat-optimized model for a conversation, but then have to switch to a completely separate reasoning model just to solve a complex math problem.
Exactly. Qwen3 is designed to handle that transition internally, seamlessly. This integration provides really unprecedented flexibility. It streamlines workflows and significantly enhances usability for a huge array of tasks. It's about creating a single brain that can effectively shift gears on demand.
And the practical benefit of that, I mean, it can't be overstated, can it?
Right.
Developers and users get this ability to adapt the model's behavior seamlessly, tailoring its approach for specific tasks on the fly, all within the same model instance.
Whether you need that quick, direct, intuitive answer for a simple query or a deeply reasoned multi-step solution for a complex analytical problem, the model can adjust.
Without needing you to reconfigure your whole setup or choose a different model, that capability fundamentally changes how we interact with and deploy LLMs, doesn't it? Moving towards a more fluid, more responsive AI assistant.
It really does. Okay, next up, the thinking budget mechanism. This is another really innovative feature. It gives users this fine-grained control over the level of reasoning effort the model applies during task execution.
So you can sort of dial the thinking up or down.
Kind of. Think of it as allocating a specific amount of computational brain power for a given problem. It's a very direct approach to resource optimization. By explicitly setting a budget for the computational resources, which in this context is often measured by the number of tokens the model is allowed to generate for its internal thought process, users can directly influence the model's inference process.
And this isn't just theoretical, right? It has real-world implications.
Oh, absolutely. Tangible implications for deployment?
Because this mechanism really highlights that crucial trade-off that practitioners, grapple with every day. Users can now consciously balance inference latency, how fast they get an answer, and the overall performance or depth of the answer, based on the specific complexity and the real-time needs of their application.
Yeah, you could imagine telling the model, for this quick summarization task, spend minimal compute on thinking, versus, okay, for this medical diagnostic reasoning problem, allocate a much larger budget to ensure really thorough thought.
It's about adaptively allocating those computational resources during inference to get the best outcome for your specific constraints, rather than just having a one-size-fits-all approach. It allows this level of granular control over the AI's thought process that just wasn't really available before.
Precisely. It allows efficiency where needed and depth where it's critical.
Okay.
Okay, the third pillar is the massive multilingual expansion.
Right, this is a big jump.
Huge jump. Qwen3 dramatically increased its language support, going from 29 languages in its predecessor, Qwen 2.5, to a remarkable 119 languages and dialects.
Oh, 119.
Yeah. And this isn't just about, superficial translation capabilities. This significant investment directly enhances global accessibility and reflects a substantial improvement in its cross-lingual understanding and generation capabilities. The goal seems to be truly global communication and problem solving, really breaking down linguistic barriers in AI applications.
And to put that expansion into perspective, it's not just a list of languages. It's backed by an enormous pre-training effort, right? I think the paper mentioned something like 36 trillion tokens.
That's right, an astonishing 36 trillion tokens across these 119 languages. That foundational scale is exactly what enables such robust and deep multilingual performance. It allows the models to understand nuances and generate high-quality text across a truly diverse linguistic landscape. It's a testament to the comprehensive approach they took to global language proficiency.
Okay, and the final point on the vision was around efficiency for the smaller models.
Yes, exactly. For efficiency, particularly concerning the smaller models within the Qwen3 family, they leverage strong tweak distillation.
Okay, so distilling knowledge from the big models to the small ones.
Precisely. This technique is designed to significantly reduce the computational resources and, frankly, the sheer development effort required to build highly capable, smaller-scale models.
Yeah.
And it's not just about making them perform adequately, it's about ensuring they maintain highly competitive performance against larger models in their class.
So it's about transferring that knowledge, those nuanced problem-solving strategies, from the flagships down to the lightweights.
Exactly. It allows these smaller models to effectively punch above their weight class in terms of capability, while remaining highly efficient for deployment on less powerful hardware or, for cost-sensitive applications.
Okay, so that's a really comprehensive vision. Unified thinking, adaptive resources, massive multilingual support, and efficient scaling down. With that blueprint in mind, let's lift the hood now and look at the engineering that makes it all possible, the architectural foundations.
Right, how these principles are actually embedded in the design of the models, both the dense and the mixture of expert types.
Section 2, architectural foundations, dense, MOE, and innovations.
Yeah.
Let's start with just outlining the series again. It's quite a family.
It is. As you said, 6 dense models, Qwen 3.6b, 1.7b, 4b, 8b, 14b, and 32b. These are the more traditional monolithic neural networks.
And then the 2 MOE models.
Yes, Qwen 330b, A3b. And the big one, the flagship, Qwen 3 235d, A22b.
And that flagship, the 235B, A22B, is the primary MOE model, right? 235 billion total parameters, but only 22 billion activated per token.
Correct. That design really reflects their commitment to hitting that sweet spot between immense scale in potential knowledge and exceptional efficiency during operation. It's a tough balance to strike.
So, looking at the Qwen3 dense model architecture, you mentioned it builds on Qwen 2.5.
Largely, yes. Many core architectural elements that have proven effective in scaling LLMs were retained. Things like grouped query attention, GQA, which is crucial for efficient attention mechanisms.
Right, helps process token relationships faster with less memory.
Exactly. They also kept switch-ear-U as their activation function, which is popular and known for performance benefits. Rotary positional embeddings, or ROPE, are still there too, crucial for handling positional info in sequences.
Letting the model understand word order without fixed encodings.
And finally, RMS norm with prenormalization is used to maintain stable training dynamics, which is vital for these really deep neural networks.
But they didn't just copy it wholesale. There were some specific strategic changes in Qwen3, right?
Yes, a couple of notable ones. They opted for the removal of the QKV bias, which was present in Qwen 2. This suggests a simplification in that part of the attention mechanism, potentially reducing complexity, maybe without hurting performance.
Interesting. And the other change?
They introduced QK-norm into the attention mechanism. This seems like a strategic addition specifically aimed at ensuring even more stable training, especially as these models get bigger and deeper. It's crucial for preventing numerical instabilities during optimization.
Okay, so refinements for stability and maybe simplification. How does this architecture look across the different sizes of dense models?
Well, it scales quite logically. For instance, the smaller ones, Qwen3 0.6b and 1.7b, they have 28 layers, 16 query heads, 8 key value heads. They also use tied embeddings, input and output layers, share weights, and they support a 32K token context length.
And as they get bigger, say the 4B up to the 32B.
As they scale up, the architecture adapts. The number of layers increases, from 36 in the 4B up to 64 in the 32B. Query heads also increase from 328 in the 4B to 648 in the 32B.
And they ditch the tied embeddings for the larger ones.
Yes, for the 4B and larger, embedding tying is removed, likely needing more distinct representations. And crucially, these larger dense models support a significantly extended context length, 128,000 tokens.
Wow, 128K.
Yeah.
That's substantial. It really shows how they tailored the architecture across the spectrum.
Definitely. Okay, moving to the Qwen3 MOE model architecture. It's important to reiterate, these share the same fundamental backbone as the dense models. GQA, SWIGLU, ROPE, RMS-norm are all there.
But they have their unique MOE characteristics.
Exactly. Tailored for that specialized efficiency you get with MOE. They specifically follow the Qwen 2.5 MOE implementation of fine-grained expert segmentation,
which helps distribute specialized knowledge more granularly.
Precisely. Both MOE models in Qwen3 have a total of 128 experts, which is quite a few, each capable of specializing. But critically, only 8 experts are activated per token during inference. That's the cornerstone of their efficiency.
Only 8 out of 128.
Yes. It lets the model selectively engage only the most relevant experts for any given input. And interestingly, a notable change from Qwen 2.5 Mo is that the Qwen3 Mo design excludes shared experts.
No shared experts. Why that change?
It might simplify the expert routing mechanism, potentially leading to clearer, more distinct specialization among the experts.
Okay. And what's the practical upshot of this design, particularly adopting that global batch load balancing loss? What does that do?
Yes. That mechanism is really important. It encourages expert specialization by essentially preventing all the experts from trying to learn the same general things. It pushes them to specialize in distinct areas of the data distribution.
You get unique capabilities from each expert.
Exactly. And that specialization, combined with the efficient sparse activation, is really fundamental to the MOE's effectiveness. It allows them to scale capabilities way up without linearly scaling the inference costs. It's a smart way to maximize the collective intelligence of all those experts.
Got it. So can you give us the specs for the MOE models like you did for the dense ones?
Sure. The Qwen3 30B A3B model, the smaller MOE, has 48 layers, 32 query heads, and 4 key value heads. Its bigger sibling, the flagship Qwen3 235B A22B, scales way up to 94 layers and 64 query heads with 4 key value heads.
94 layers, wow.
Yeah, it's deep. But despite their different scales, both consistently use that 128 total experts, 8 activated per token design. And both also support that impressive 128,000 token context length.
So consistency in the core MOE principles across sizes.
Exactly. It shows confidence in that underlying design, balancing huge capacity with controlled computational cost.
And just quickly, the tokenizer. Still the same Qwen tokenizer.
Yes, they continue to use the established Qwen tokenizer. It employs byte-level byte-pair encoding, BBPE.
Which is good for handling arbitrary text, especially multilingual data, right? No unknown tokens.
Correct. And it has that substantial vocabulary size of 151,669, making it really robust and foundational to Qwen3's broad language handling and text processing efficiency.
Okay, that gives us a solid understanding of the architectural blueprint. Now, let's transition to the rigorous training regimen that actually shapes these models. This is where the raw data gets turned into refined intelligence.
Absolutely. This is where we understand the immense effort and sophisticated methods behind their capabilities. It's a fascinating journey.
Section 3, the rigorous training regimen, from data to refinement. Let's start with the foundation, pre-training.
Right, pre-training, laying the foundation. And a huge aspect here, a major leap from Qwen 2.5 is the expanded data scale and diversity.
Twice as many tokens, you said.
Yes, compared to Qwen 2.5, Qwen 3 was pre-trained with a data set twice as large as staggering 36 trillion tokens in total. And this huge corpus also covers 3 times as many languages now, up to 119 languages and dialects. Truly global coverage.
And it's not just big, it's curated, right? High-quality stuff.
Exactly. It's meticulously curated to include high-quality content across diverse domains. Coding, STEM, complex reasoning tasks, huge collections of books, substantial multilingual data, and also a significant amount of carefully generated synthetic data. This breadth and depth are just fundamental to its versatile capabilities.
How did they even manage to get that much data, especially high-quality data? You mentioned a multimodal approach.
Yes, they employed some pretty innovative data engineering. For instance, they fine-tuned Qwen 2.5 VL, their vision language model, to effectively extract high-quality text from an enormous volume of PDF-like documents.
So pulling text from images of text, essentially.
Right, and then they used Qwen 2.5 itself to further refine that extracted text, enhancing its quality for language model training. And synthetic data generation played a really crucial role, too.
Using specialized models to create data.
Exactly. They use domain-specific models like Qwen 2.5 Math for generating high-quality mathematical content and Qwen 2.5 Coder for code-related data. These specialized models generated trillions of text tokens in various useful formats: textbooks, Q&A pairs, instructions, code snippets covering dozens of domains. This targeted synthetic data creation significantly boosted the model's proficiency in those challenging areas.
Okay, so they have this massive, diverse data set. How do they manage it all effectively during training? You mentioned a sophisticated annotation system.
Yes, a sophisticated multilingual data annotation system. This was developed and applied to over 30 trillion tokens within their pre-training data sets. It meticulously annotates the data across multiple dimensions, things like educational value, specific fields, domains, even safety considerations.
And these detailed annotations are key for filtering and mixing the data.
Absolutely crucial. They support more effective data filtering and much more intelligent combination strategies during training. And unlike some previous studies that optimize data mixtures at a broader source or domain level, Qwen3's method refines the data mixture at the instance level.
Instance level, so token by token almost.
Well, maybe not token by token, but at a much finer granularity than just use this much web text, this much book text. They achieved this through extensive ablation experiments on small proxy models, leveraging those fine-grained labels. This ensures a much more precise and effective data distribution, ultimately leading to a more balanced and capable model.
Okay, that makes sense. And the pre-training itself wasn't just one big run, right? It was staged.
Correct. A systematic, three-stage pre-training process. It's like a carefully orchestrated curriculum designed to build capabilities progressively. Stage 1 is the general stage.
Laying the broad foundation.
Exactly. Models are initially trained on over 30 trillion tokens using a sequence length of 4,096. This stage is all about establishing that robust foundation of general knowledge and language proficiency across all 119 languages. Basic world understanding, fundamental linguistic competence.
Okay, stage 1, general knowledge. What's stage 2?
Stage 2 is the reasoning stage, S2. Here, the focus strategically shifts. The models get further pre-training, but on a smaller subset, about 5 trillion tokens of higher quality data.
Higher quality meaning more focused on certain areas.
Precisely. The corpus for this stage is specifically optimized with an increased proportion of STEM content, coding examples, reasoning tasks, and that curated synthetic data we talked about. It's all aimed at significantly enhancing the model's complex reasoning abilities.
And they tweak the training parameters here, too. Faster learning rate decay.
Yes, during this stage, they accelerate the learning rate decay. This helps fine-tune the learning process, allowing the model to converge more effectively on these specialized reasoning tasks.
Makes sense. So general, then reasoning. What's stage 3?
Stage 3 is the long context stage. Here, the models are trained on hundreds of billions of tokens, specifically from high-quality long-context corpora. The goal is explicitly to extend their maximum context length from that initial 4,096 tokens up to an impressive 32,768 tokens.
Which is critical for understanding long documents or conversations.
Absolutely. And the data mix here is specific. 75% of the text is between 16K and 32K tokens long. The rest is between 4K and 16K. So a rich diet of genuinely long documents.
And getting that long context to work well usually requires special techniques, right? You can't just feed longer sequences into the same architecture.
Correct. They employed several advanced techniques. They increased the base frequency of rope from 10,000 to 1 million using ABF, absolute base frequency.
Which helps rope extrapolate better to longer sequences.
Exactly. And additionally, they introduced yarn Yet another rote-based near-linear and dual-chunk attention, DCA. Yarn adapts rote for longer context by dynamically adjusting things, while DCA improves efficiency by processing context chunks in parallel.
And together, these give a big boost to the usable context length during inference.
A fourfold increase in sequence length capacity, specifically during inference. That's critical for making long context practical, avoiding performance degradation or memory issues when handling massive inputs.
Okay, and underlying all these stages, there was careful hyperparameter tuning.
Oh, yes. Meticulous hyperparameter optimization. Similar to Qwen 2.5, they developed sophisticated scaling laws to predict the optimal hyperparameters, things like learning rate schedules, batch sizes across these three distinct stages.
Based on lots of experiments.
Extensive experiments, yeah. Systematically studying the complex interplay between architecture, data, training stage, and the optimal settings. This empirical data-driven approach ensured each model, dense or MOE, was trained using the most effective strategy for its specific configuration, maximizing learning potential and stability.
All right, that covers the massive pre-training effort. Now, let's move on to post-training. This is where the models get refined, aligned with human preferences, and those special capabilities are really honed.
Exactly. And there are two main goals here. First, thinking control. Integrating those non-thinking and thinking modes seamlessly and giving users control via the thinking budget.
And second?
Second, strong to weak distillation. Streamlining the post-training for the lightweight models by transferring knowledge from the bigger ones.
Okay. And the flagship models have their own specific post-training pipeline.
Yes, a sophisticated four-stage training process for the flagships. It's crucial for their dual-mode capabilities. The pipeline is carefully structured. The first two stages focus primarily on developing deep thinking abilities, emphasizing complex reasoning.
And the next two stages?
The subsequent two stages focus on integrating robust, non-thinking functionalities, ensuring those quick, direct responses. This progressive approach aims for a balanced development of both modes, making the model both a fast responder and a deep thinker.
Okay, let's break down those four stages for the flagships. Stage one.
Stage one is the long-caught cold start. This starts with meticulously curating a comprehensive dataset spanning demanding domains: math, code, logical reasoning, general STEM. Each problem is rigorously paired with verified reference answers or robust code-based test cases. Impeccable ground truth.
So this is the initial exposure to structured reasoning, the chain of thought stuff.
Right. It forms the foundational cold start for long chain of thought or long-caught training.
And the dataset curation involves some heavy filtering.
Extremely rigorous two-phase filtering. First, query filtering, using Qwen 2.572b instruct as an assistant. It removes unverifiable queries or ones that don't need two-phase reasoning.
So only genuinely complex problems requiring thought get through.
Precisely. And domains are annotated for balance. Then, response filtering. They generate candidate responses using QWQ32b. If that fails, humans step in. If it succeeds, strict criteria are applied to weed out incorrect, repetitive, or stylistically poor responses.
And the goal here isn't peak performance yet. It's about teaching the pattern of reasoning.
Exactly. Instilling foundational reasoning patterns, minimizing initial training samples, teaching the model how to think, not just what to think.
Got it. Stage one, cold start for reasoning patterns. Stage two.
Stage two, reasoning RL, reinforcement learning. Now we focus on developing strong reasoning abilities. The query verifier pairs used here are distinct from the cold start set.
How are they chosen?
They're selected to be learnable for the cold start model, but also challenging, pushing its boundaries. And they cover a broad range of subdomains to generalize reasoning. They collected about 3,995 such pairs.
And they use GRPO for the RL updates.
Yes, GRPO, Generalized Policy Optimization. They found that using a large batch size, high number of rollouts per query, and off-policy training for sample efficiency significantly helped the training.
Making it learn from more experiences. And they manage the exploration-exploitation trade-off.
Yes, by carefully controlling the model's entropy, keeping it stable or steadily increasing. This avoids constant manual hyperparameter tuning, which can be a real bottleneck in RL.
Did it work? Did the reasoning improve?
Dramatically. As a direct result, the AME 24 score for Qwen3 235b A22b jumped impressively from 70.1 to 85.1 over just 170 RL steps.
Wow, that's a big gain on a tough benchmark. Shows the effectiveness of this stage.
Definitely. Okay, on to stage 3, thinking mode fusion. The main goal here is to seamlessly integrate the non-thinking capabilities into the reasoning model developed so far.
So this is where the two modes come together in one model.
Exactly, enabling that unified management and control. This fusion is achieved through continual supervised fine-tuning, SFT, on the reasoning RL model, combined with a specially designed chat template that acts as the interface between the modes.
And they found that models good at both modes performed well across different thinking budgets.
Yes, that emerged naturally, highlighting the power of true integration.
How did they construct the SFT data for this fusion stage?
It was quite clever and multifaceted. They combined thinking data, essentially the best examples of reasoning generated via rejection sampling from the stage 2 model's outputs, with non-thinking data.
And the non-thinking data covered a wide range.
Very diverse. Coding, math, general instruction following, multilingual tasks, creative writing, Q&A, role-playing. The quality was rigorously checked with auto-generated checklists, and importantly, they significantly increased the proportion of translation tasks for low-resource languages to boost global accessibility.
Okay. And the chat template design is key for controlling this.
Absolutely central. The chat template design uses flags like think, which is the default, and no think in user queries. For non-thinking mode, an empty thinking block is kept internally for format consistency, even if nothing is shown. In multi-turn chats, the model just follows the last flag used. It's the direct interface for users to tap into Qwen3's dual modes.
What really caught my eye here was the emergent thinking budget control. You're saying this wasn't explicitly trained.
That's right. It seems that once the model learns to respond well in both modes, it naturally develops the ability to handle intermediate cases, generating responses based on incomplete or partial thinking.
How does that work?
When the model's internal thinking hits a user-defined threshold, like a token count or time limit, the process is manually halted, a stop instruction is inserted, and the model generates its final response based on whatever reasoning it managed up to that point.
So you get dynamic, on-the-fly control over thinking depth, even mid-generation. That's incredibly flexible.
It's a very powerful emergent capability. Okay, the final stage for flagship, stage 4. General RL reinforcement learning.
Another RL stage. What's the focus here?
The stage aims to broadly enhance capabilities and stability across diverse scenarios, moving beyond just reasoning to encompass broader utility. They used a sophisticated, multifaceted reward system covering over 20 distinct tasks with custom scoring criteria.
Targeting core capabilities like
instruction following, content, format, length, accuracy, format following, correct use of flags like think, no think, and tokens like think, think, preference alignment, helpfulness, engagement, style for open-ended queries, agent ability, correctly using tools, multi-turn interaction with feedback, and also abilities for specialized scenarios like RG to guide accurate responses and minimize hallucination.
That's a lot to reward for. How did they provide the reward signals?
They used 3 distinct types of rewards, strategically. First, rule-based rewards, especially for reasoning, instruction following, format adherence. These are precise and good at preventing reward hacking.
Where the model games the system.
Exactly. Second, model-based rewards with referenced answers, using Qwen 2.572b instruct to score responses against a reference. This is flexible for diverse tasks without strict formatting. And third, model-based rewards without reference answers.
How does that work?
They trained a separate reward model using extensive human preference data to assign scalar scores. This enhances engagement, helpfulness, and alignment for broader, open-ended queries where there isn't one single correct answer. This layered reward system really shows the complexity of aligning AI with human preferences.
Okay, that covers the intensive 4-stage process for the flagships. What about the lightweight models? That was the strong-to-weak distillation pipeline.
Correct. An innovative strong-to-weak distillation pipeline specifically designed for the 5 smaller, dense models, 0.6b to 14b, and the Qwen3 30b A3b MOE model. The goal is to boost their performance and give them robust mode-switching capabilities, so even smaller models get the dual-mode intelligence.
And this had 2 phases.
Yes, 2 primary phases. First, off-policy distillation. Here they take the outputs generated by the stronger teacher models, Qwen3 32b or Qwen3 235b A22b, in both think and no-think modes, and combine them for response distillation.
So the student model learns from the expert's examples in both modes, builds the basic skills.
Exactly. Lays that solid foundation for reasoning and mode switching. It's like giving the student a comprehensive textbook of expert thought.
Okay, phase 1. Learning from examples. Phase 2.
Phase 2. On-policy distillation. Now, the student model actively generates its own sequences for fine-tuning. It shifts from passively observing to actively practicing.
How does that work?
Prompts are sampled. The student generates responses in either think or no-think mode, trying out its knowledge. Then, it's fine-tuned by aligning its logits, the raw outputs, with the logits of the stronger teacher model, 32B or 235B, to minimize the KL divergence.
Aligning the student's internal thinking with the teacher's. And this is efficient.
Remarkably efficient. It achieves significantly better immediate performance, higher pass at 1 scores, meaning more problems solved correctly first time. And crucially, it also expands the student's exploration space better, pass at 64 results, suggesting better potential for finding solutions eventually.
And the cost saving.
All of this is achieved with approximately 1/10 of the GPU hours compared to applying the full 4-stage RL method directly to these small models.
1/10. That's huge. Makes it incredibly cost-effective to get advanced capabilities into smaller models.
It really does.
Okay, this detailed training regimen sounds incredibly comprehensive and, resource-intensive. After all that meticulous design and grueling training, the moment of truth arrives. How does Qwen3 actually perform when you put it up against the best? Let's turn to the empirical validation, starting with the pre-trained base models.
Right, where the rubber meets the road on the benchmarks.
Section 4, empirical validation pre-trained model performance.
Indeed. So a comprehensive evaluation of the base models was conducted to really understand their foundational capabilities before any instruction tuning or fine-tuning. The evaluation focused specifically on assessing intelligence across key areas: general knowledge, reasoning, math, scientific knowledge, coding, and multilingual capabilities.
A broad scope to get a holistic view.
Exactly, ensuring a holistic understanding across diverse cognitive tasks.
And they used a lot of benchmarks for this.
A robust set of 15 benchmarks, each chosen to probe different facets. For general tasks, MMLU, MMLU Pro, MMLU Redux, BBH, Super GPQA. For math and STEM, GPQA, GSM-8K, math. For coding, EVOL Plus, Multi-PLE, MBPP 3-Shot, CRUXO. And for multilingual, MGSM, MMMLU, including.
Quite the gauntlet. And the emphasis was on fair comparison.
Critical point. Emphasis on fair comparison through standardized evaluation settings across all models, ensuring valid conclusions could be drawn.
Who were they comparing against?
The Qwen3 series was pitted against its predecessor, Qwen 2.5, naturally, and other leading open-source base models. Think DeepSeek v3 base, models from Gemma 3, and various base models from Llama 3 and Llama 4. Comparisons were meticulous, considering parameter scales to get a truly representative picture of their standing.
Okay, so what were the key conclusions from this pre-training bake-off?
First and foremost, the Qwen3 235B A22 base model emerged as a dominant performer. It consistently outperformed previous open-source state-of-the-art dense and MOE base models across the vast majority of tasks.
Outperforming models like DeepSeek v3 base, Llama 4 Maverick base.
Yes, and Qwen 2.572B base. And what's particularly striking is that it achieved this while using significantly fewer total or activated parameters. That highlight a substantial efficiency advantage, suggesting a more optimized architecture and training process. More bang for your buck, computationally speaking.
That efficiency point seems really strong. You mentioned specific comparisons, like against Llama 4 Maverick base.
Right. Despite having about half the total parameters of the recently open-sourced Llama 4 Maverick base, Qwen3 235B A22B base still showed superior performance on most benchmarks.
And against DeepSeek v3 base.
Even more impressive, it outperformed DeepSeek v3 base on 14 out of 15 benchmarks, while using only about 1/3 the total parameters and 2/3 the activated parameters. That makes a very strong case for its cost effectiveness.
It also beat Qwen 2.5 Plus, a similar-sized MOE.
Yes, significantly outperformed it with fewer parameters. And compared to the previous flagship dense model, Qwen 2.572B base, the new MOE surpassed it in all benchmarks, using less than 1/3 the activated parameters. That translates directly to much cheaper inference and training. It really feels like a potential game changer for deployment costs. And this leads right into the second major conclusion. The Qwen3 MOE-based models demonstrate unprecedented efficiency. The results are quite clear.
How efficient are we talking?
Well, first, using the exact same pre-training data, Qwen3 MOE-based models achieve similar performance to Qwen3 dense-based models with only 1/5 of the activated parameters.
1/5. That's a huge efficiency leap for comparable capability.
Massive. Second, due to architectural improvements, more training tokens, advanced training strategies, Qwen3 MoE-based models demonstrably outperform Qwen 2.5 MoE-based models with less than half the activated parameters and fewer total parameters.
Just significantly better than the previous MoE generation, too.
Yes. And perhaps most astonishingly, even with just 1/10 of the activated parameters of the Qwen 2.5 dense-based model, a Qwen3 MoE-based model can achieve comparable performance. This provides huge advantages in inference and training costs, making high-performance AI more accessible and sustainable.
Okay, the MoE efficiency story is compelling. But it wasn't just the MoEs that improved, right? The Qwen3 dense-based models also showed a significant performance leap.
They did. Overall, their performance is comparable to Qwen 2.5 models, but at higher parameter scales in the older generation.
Meaning a smaller Qwen3 dense model performs like a larger Qwen 2.5 dense model.
Exactly. For instance, Qwen3 1.7b base is comparable to Qwen 2.53b base, Qwen3 4b base to Qwen 2.57d base, and so on, up to Qwen3 3.2d base being comparable to Qwen 2.572b base. You're getting the power of a larger previous gen model in a smaller, more efficient Qwen3 package.
That's a solid improvement across the board.
And crucially, when you zero in on benchmarks specific to STEM, coding, and reasoning, those areas needing deliberate thought, the Qwen 3 dense base models even surpass Qwen 2.5 base models at higher parameter scales.
So targeted improvements in complex problem-solving areas.
Yes, it indicates a fundamental improvement there, showing the new architecture and training are yielding better results where it really matters for complex tasks.
Can you give us some highlights for specific models, like the biggest dense one, Qwen3 32b base?
Sure. Qwen3 32b base notably outperforms Qwen 2.5 32bb and Gemma 327b on most benchmarks. Even more impressively, it's competitive against Qwen 2.5 72b base, actually beating it in 10 out of 15 benchmarks despite having less than half the parameters.
That's strong. How about against MoE models?
It significantly outperforms the MoE model Llama 4 Scout base. Interestingly, Qwen 332b does this with only 1/3 the total parameters of Llama 4 Scout, but it uses twice the activated parameters. It really demonstrates an impressive balance of efficiency and capability for its size as a dense model.
Okay, what about the mid-range?
Yeah.
Qwen 330b base and the smaller MoE, Qwen 330b A3b base.
The Qwen 314b base shows a clear, significant performance advantage over Gemma 312b and Qwen 2.5 14b on all benchmarks. But what's really striking is Qwen 330b A3b.
The smaller MoE, yeah.
Right. Despite having only 1/5 the activated non-embedding parameters compared to QWQ32b, it significantly outperforms Qwen 2.5 14b base across all tasks. And it achieves performance comparable to both Qwen 3 14b base and Qwen 2.5 32b base.
So lots of power in a very efficient package.
Yeah.
Great cost effectiveness.
Exactly. Huge potential for cost savings in inference and training.
And the really small ones, the edge side models.
Yes, the smaller dense models, Qwen 3.8b, 4b, 1.7b, 0.6b base, these shouldn't be overlooked, especially for practical deployments. They consistently maintain strong performance across nearly all benchmarks for their size.
And they even beat larger Qwen 2.5 models sometimes.
Remarkably, yes. Models like Qwen 3.8b, 4b, and 1.7b base manage to outperform the larger Qwen 2.5 14b, 7b, and 3b base models on over half of the benchmarks. This outperformance is particularly noticeable in STEM and coding tasks, which are typically tough for smaller models.
That really reflects the overall improvements baked into the whole Qwen 3 series, ensuring strong capabilities even at these more constrained scales.
It does.
Okay, so the pre-trained performance looks incredibly strong, establishing the raw power and efficiency. Now let's transition to the post-trained models. This is where we see how that foundation is fine-tuned for instructions and how that innovative dual-mode intelligence really comes into play in practice.
Right. Moving beyond base capabilities to align instruction-following models.
Section 5. Empirical validation post-trained model performance. How did they evaluate these?
Well, for evaluating the instruction-tuned models, they used a comprehensive suite of automatic benchmarks again, but this time specifically designed to assess performance in both the thinking and non-thinking modes separately.
Okay, testing both sides of the coin. What categories did they look at?
They strategically categorized the benchmarks to cover a broad spectrum. General tasks like MMLU Redux, GPQA Diamond, alignment tasks, IFEVAL, Arena Hard, how well they follow instructions, avoid refusals, math and text reasoning, high-level math like AME 2425, text logic like Zebra Logic, Autologi, agent encoding, BFCL v3 for tool use, live code bench, code forces ratings, and finally, multilingual tasks, instruction following, knowledge, math, reasoning across many languages.
Another comprehensive set, really testing practical utility.
Definitely. It ensures a thorough and nuanced understanding of performance in various operational contexts.
And they use specific settings for evaluation in each mode.
Yes, specific sampling hyperparameters were meticulously defined. For thinking mode, temperature 0.6, top P 0.95, top K20, encouraging more focused generation for reasoning. For creative tasks, they added a presence penalty of 1.5 to discourage repetition.
And for non-thinking mode,
Slightly different, leaning towards a bit more variability. Temperature 0.7, top P is 0.8, top K20, and again, presence penalty 1.5. And for both modes, a generous max output length of 32,768 tokens, extended even further to nearly 39K for the AIM benchmarks to allow ample thinking space.
Okay, so the big results. What were the key conclusions from this post-training evaluation?
The headline is definitely the Qwen3 235B A22B, the flagship model. It demonstrates state-of-the-art overall performance among open-source models in both thinking and non-thinking modes.
State-of-the-art in both. That's huge.
It's a monumental achievement. It not only surpasses strong open-source baselines like DeepSeek R1 and DeepSeek V3, but also proves highly competitive against leading closed-source models like OpenAI O1, Gemini 2.5 Pro, and GPT-4o. It really showcases profound reasoning and comprehensive general abilities.
Let's break that down. How did it do in thinking mode specifically?
It truly shines there, especially on tasks demanding deep logical thought. It outperforms DeepSeek R1 on a remarkable 17 out of 23 benchmarks, particularly excelling in reasoning-heavy tasks. Advanced math, complex agent stuff, intricate coding.
And again, efficiently.
Yes, that's the kicker. This superior performance is achieved with only 60% of the activated parameters and a mere 35% of the total parameters of DeepSeek R1. Exceptional efficiency and targeted intelligence. More capability with significantly less compute.
How close does it get to the big closed-source models in thinking mode?
It really narrows the gap remarkably well with models like OpenAI O1, Grok 3 Beta, Think, and Gemini 2.5 Pro. It demonstrates profound, robust reasoning.
Any specific scores that stand out?
For instance, on AIM-24, it scored 85.7 and 81.5 on AIM-25, really strong math problem solving. Its code forces rating of 2056 puts it in the 98.2 percentile exceptional coding prowess. These numbers really speak to its ability to tackle top-tier AI challenges.
Okay, that's thinking mode. How about non-thinking mode? Still impressive.
Continues to impress with its general capabilities? Yes. It exceeds other leading open-source models like DeepSeek V3, Llama 4 Maverick, and Qwen 2.572B Instruct. And perhaps most surprisingly, it even surpasses the closed-source GPT-4o 2024-1120 in 18 out of 23 benchmarks.
Wow, beating GPT-4o in non-thinking mode on many tasks.
On these specific benchmarks, yes. It suggests that even without engaging that deliberate step-by-step reasoning, the model retains an incredibly strong foundational understanding and ability to respond accurately and coherently.
So it has strong inherent capabilities even when not explicitly thinking.
Exactly. Performance examples include an Arena Heart score of 96.1, testing complex instruction following, and an Autology score of 83.3 for text-based logic. These show strong general understanding and response generation, making it incredibly versatile for everyday tasks, too.
Okay, flagship looks dominant. What about Qwen3 32B, the flagship dense model? How did it fare?
It sets entirely new benchmarks for reasoning performance at its scale. In thinking mode, Qwen3 32B outperforms QWQ 32B on 17 out of 23 benchmarks.
So it's the new state-of-the-art reasoning model at the 32B size.
Firmly positions itself as such, yes. A significant achievement for a dense model showing deep thought isn't exclusive to MOE.
And against closed source.
It competes very effectively with OpenAI O3 Mini Medium, demonstrating superior alignment and multilingual performance. This highlights its ability to deliver top-tier reasoning in a more accessible, dense package.
And in non-thinking mode.
Exhibits superior performance to almost all baselines there, too. It performs on par with Qwen 2.572B Instruct on general tasks, but shows significant advantages in alignment, multilingual, and reasoning-related tasks. This really demonstrates fundamental improvements over the Qwen 2.5 series, not just superficial gains.
Okay, how about the lightweight models? Qwen3 30B A3B and Qwen3 14B.
Both are highly competitive with QWQ 32B in thinking mode, especially on reasoning benchmarks, a testament to their effective training strategies.
And the efficiency angle here, especially for the MOE 30B.
This is particularly noteworthy and a strong validation. Qwen330B A3B achieves comparable performance to QWQ32B, but with a smaller overall size and, critically, less than 1/10 of the activated parameters.
Less than 1/10. That really proves the stronger weak distillation worked.
It's a resounding validation, yes, proving you can get significant capability and efficiency together. And in non-thinking mode, both these lightweights surpass non-reasoning baselines with significantly fewer parameters, offering impressive efficiency for common tasks.
Finally, the edge side models, 8B down to 0.6B, still holding up.
They maintain impressive performance for their size, yes. These models often outperform baselines, including larger Qwen 2.5 models, in both thinking and non-thinking modes.
Especially in STEM encoding.
Particularly noticeable in STEM encoding benchmarks. This is crucial for real-world applications on devices with limited compute.
And again, this underscores the effectiveness of that stronger weak distillation.
Absolutely. It further underscores its efficacy in building lightweight, cost-effective Qwen3 models that deliver robust performance even on constrained devices, truly democratizing access to powerful AI across more hardware.
Okay, we've covered the architecture, the training, the comprehensive performance evaluations. We've seen how Qwen3 stacks up. Now let's delve even deeper into some specialized capabilities and maybe some of the more nuanced insights from the technical report.
Right, exploring the nuances of its behavior and design.
Section 6, deeper insights and specialized capabilities. Let's start with that thinking budget. How effective is it really?
Well, the report provides a clear illustration, referencing Figure 2 in their paper. It shows Qwen3 demonstrating scalable and smooth performance improvements directly correlated with an increased thinking budget. This holds across mathematics, coding, and STEM domains.
So it's not just on-off, it's a tunable spectrum of intelligence. More budget equals better performance, smoothly.
Exactly. It tells us models can be designed not just to be smart, but to be smart on demand, with users having granular control over reasoning depth. This has huge implications for optimization balancing response time versus accuracy based on the task.
That's a crucial distinction. Moving beyond just the answer to how much effort went into it, they also noted that going beyond 32K tokens could further improve performance.
Yes, an interesting observation hinting at future research. It suggests that even with a robust budget, there might be latent capabilities unlocked with even more thinking space.
Does that imply a future where we might dynamically bid for compute, like an internal auction for thinking within the model, depending on the task's importance or maybe the user's patience?
That's a fascinating way to frame it, absolutely, a possibility. The report also gives significant insights into the effectiveness and efficiency of on-policy distillation.
Right, the comparison between distillation and direct RL for the smaller models.
Yes. A direct comparison shows distillation achieves significantly better performance than direct RL for math and code queries. But here's the kicker. It does so while requiring only about 1/10 of the GPU hours.
1,800 versus almost 18,000 GPU hours. A massive efficiency gain without losing quality.
Huge. It demonstrates strategic knowledge transfer can be far more effective than just brute force fine-tuning for certain domains.
And distillation also helps with exploration, right? Not just getting the first answer right.
Crucially, yes, it expands the student model's exploration space, enhancing its reasoning potential. This shows up in significantly improved paths at 64 scores on AIM-24 and AIM-25. The distilled models are better at exploring different solution paths, key for complex problems.
And RL alone didn't give that exploration boost.
Interestingly, no. It highlights distillation's unique advantage in broadening a model's problem-solving strategies. It's like teaching it how to learn, not just facts.
Okay. What about the effects of thinking mode fusion and general RL, those later stages in the flagship training?
They analyzed Qwen332B's performance at different post-training stages, using some in-house benchmarks too, like counterfact QA, factual consistency, length Sorol, length adherence, think follow, mode switching accuracy, and tool use, agent skills.
What did stage 3, the thinking mode fusion, achieve?
It established the initial mode switching ability think follow score of 88.7, so mostly getting cues right. And it significantly enhanced general and instruction following capabilities in thinking mode, big jumps on counterfact QA and length Sorol. So initial success in using reasoning for broader tasks.
In stage 4, the general RL.
That further strengthened general instruction following and agent capabilities in both modes. It refined overall utility. Notably, the think follow score jumped dramatically to 98.9.
Wow, almost perfect mode switching. Critical for user experience.
Very accurate and consistent switching based on user prods.
Well, there was that interesting performance trade-off.
Yes. This is fascinating. For the core knowledge, STEM, math, and coding tasks, these last two stages, thinking mode fusion, general RL, did not bring significant improvements. In fact, for really tough tasks like AIM-24 and Live Code Bench, performance in thinking mode actually decreased slightly after these stages.
That is surprising. Why would that happen?
Their hypothesis is that training on a broader range of general tasks while enhancing overall versatility might inadvertently compromise some of the highly specialized capabilities needed for peak performance on those very narrow, complex problems.
So a trade-off between broad utility and peak specialized performance.
Exactly. A trade-off they consciously accepted to make the model more versatile overall. For you listeners working with these models, it highlights a crucial decision point. Prioritize broad applicability or razor-sharp focus for specific, challenging domains. It speaks to that ongoing tension between specialization and generalization in AI development.
A really important consideration. Okay, what about long context ability?
The ruler benchmark results clearly show Qwen3's capabilities here. They used yarn with a scaling factor of 4 for impressive length extrapolation, handling inputs much longer than initially trained on.
And how did it compare to Qwen 2.5?
In non-thinking mode, Qwen3 models consistently outperform Qwen 2.5 models of similar size on long context tasks. A significant improvement in efficiently handling long inputs for tasks like summarization or extraction.
It's a slight dip in thinking mode for these tasks.
Yes, a slight performance degradation was seen in thinking mode specifically for these retrieval-heavy tasks. The hypothesis is that the explicit thinking content, while great for reasoning, might actually interfere or add noise when the task is just straightforward information retrieval from a long text.
So the internal thoughts might distract from just finding the answer in the text?
Potentially, yes. It highlights an interesting area for future refinement. How to make thinking mode selectively beneficial, avoiding interference where it's not needed.
Makes sense. Lastly, multilingual ability. The report showed lots of tables.
Yes, comprehensive benchmark scores across numerous languages: Spanish, French, Portuguese, Italian, Arabic, Japanese, Korean, Indonesian, Russian, Vietnamese, German, Thai. The results unequivocally demonstrate strong multilingual capabilities across the Qwen3 series, a testament to that 119-language pre-training. Truly a global language model.
And they use the Bellabel benchmark for broader coverage.
Right. Bellabel assesses understanding across 80 supported languages and their families, giving a comprehensive view of cross-lingual proficiency.
And their skills.
Confirmed Qwen3's competitive standing. It achieves comparable performance to similarly sized Gemma models while significantly outperforming Qwen 2.5 on Bellabel. This validates the huge investment in linguistic coverage and deep cross-lingual understanding, crucial for truly global AI applications.
Okay, fantastic overview. Let's wrap this up.
Sounds good.
So what's the practical upshot of all this for you, our expert listener? We've taken this deep dive into the Qwen3 Technical Report, and what really stands out is just how comprehensive this model family is. We've covered its innovative dual thinking, non-thinking modes, that adaptive thinking budget giving fine-grained control, the truly massive multilingual support across 119 languages.
And its consistently strong performance across both the pre-trained base models and the post-trained instruction-tuned models.
Absolutely. All of this really solidifies its position as a state-of-the-art open-source LLM, pushing the boundaries of what's possible in the open ecosystem.
Yeah, the key innovations here, that dynamic mode switching, the resource optimization via the thinking budget, and the clear success of strong to weak distillation for creating these remarkably efficient, lightweight models, they've collectively set a new benchmark for accessible, powerful AI. This work is really a testament to the accelerating pace of open source development, proving collaboration and innovation can seriously challenge proprietary systems.
And they're not stopping here, right?
Yeah.
What's next for Qwen?
No, they outlined clear future research paths. They plan to continue scaling up pre-training with even higher quality, more diverse data. They'll focus on improving architecture and training methods for better compression and scaling to extremely long contexts way beyond the 128K we discussed.
And more focus on RL and agents.
Yes, increasing computational resources for reinforcement learning with a particular emphasis on agent-based RL systems learning directly from environmental feedback, moving towards more autonomous interactive AI.
So the aim is building increasingly sophisticated agents, capable of tackling complex tasks needing dynamic inference scaling and real-world interaction. It's clear the evolution towards more autonomous, adaptable, genuinely intelligent systems is very much ongoing.
It is. And this raises, I think, an important question for you to consider. How does this explicit control over thinking in models like Qwen3, combined with adaptive resource allocation, fundamentally change our understanding of intelligence in AI?
Good question. Is it a step towards more transparent AI reasoning?
Is it? And what implications does that hold for designing future AGI systems where understanding and managing the thought process could be absolutely paramount? And maybe even more excitingly, how might these fine-grained controls, the thinking budget, the mode switching enable entirely new categories of applications, new problem-solving paradigms we haven't even conceived of yet, allowing AI not just to give answers, but to manage its own cognitive load in completely novel ways?
Powerful questions to ponder as these incredible models continue to advance and reshape our technological landscape. Thank you for joining us on this deep dive into the Qwen3 Technical Report. We definitely encourage you to explore these ideas further, maybe even dig into the paper itself for more fascinating details.